Good morning and good evening, ladies and gentlemen. Today, I'm going to introduce a new technique, which is called the automatic seismic horizon recognition from seismic data using correlation exponent and its higher order. A case study of Parihaka field, offshore Taranaki Basin, New Zealand. The aim of this research is identifying the stratigraphic markers by using seismic data in automated mode. And this automation would be achieved through the application of correlation or a scaling exponent and its higher order. The objective of this work is to examine the scaling exponent and its higher order on the synthetic data, and through this way, identify the most convenient parameters for the further work, for the main work, and to apply the technique to the post-stack 3D seismic data and estimate the possibility of detection of the main geological features like horizons, faults, bright spot anomalies, etc. Methodology for defining inlines or cross lines and capturing the information seismic from seismic data. We used OpenDetect software. For reading SegWi files and for seismic traces extraction and calculation of scaling exponent and its higher order derivative, we used a code that was written in MATLAB. For define the trace number from inline and crossline numbers, we used a program called SegWi Detective. And for exhibition of the results, for representation of the results, we used a program Surfer 13. Let us talk about automated stratigraphic layer detection using combined scaling exponent and its double derivative or higher order. Let us look through the theory of this method. Let us suppose that there is a length of 30 meters, and we can measure this length through a length scale with 5 meters. Our ruler size is, or length scale, it is 5 meters. And n is the number of length scales to map the length L. So to measure length of 30 meters, we need to use our ruler, our length scale, 6 times. 1, 2, 3, 4, 5, and 6. So the number of length scales will be 6. But let us suppose that our length scale will be 6 meters. In this case, we need to measure this length of 30 meters 5 times. 1, 2, 3, 4, 5. And the number of length scales to map the length L will be 5. And what we can observe that with the decrease in the length scale, the number of length scales to measure some kind of length will be increased. And on the contrary, with the increasing of length scale, we can measure the same length with the less number of times. So, and we can conclude that these parameters are inversely proportional. And they, on the screen, you're able to see their relationship because they are reversely proportional. You're able to see C, it is their proportionality constant, and alpha are length scale in the power of alpha, where alpha is the scaling exponent. It is a parameter that we will use in our research. Let us talk about the correlation integral. On the screen, you are able to see the formula of this correlation integral, where n is the number of pairs of digital values of seismic trace. In our case, it was 1,225. So below, you're able to see the formula from which we calculated this number of pairs, where factorials of n and k. and n minus k, where n is the number of events. In our case, it is 50. It will be our length scale or window length. And k is the number of pairs. Our number of pairs is 2. That's why we calculated the number of pairs, 1225. R is the length scale, or further we will call it window length. Rij is the distance between any 2 points of the cluster set obtained using the distance formula, with using time values and amplitude values. And H is the Heaviside step function. It is equal to 0 when Rij less than the length scale, and equal to 1 for Rij more than R. And through this formula, it is possible to bind correlation integral and length and scaling exponent. They are connected through length scale, and correlation integral is connected with the scaling exponent. And we would like to present another parameters that we will use in our research. It is a double derivative. Below, you are able to see the formula of a double derivative, where we used the values of scaling exponent and the length scales in different points, in points I and j. So let us look through the previous research. The scaling exponent was presented by Grassenberg and Prakashia in 1983 for the first time. Garyanov in 1997 proposed that fractal nature is a universal property of the continent crust. After that, earthquake and microseismicity patterns of underground mines gave the robustness use of the correlation integral technique. Mondal and Roy, Roy and Gupta, and Roy and Pandhi, Roy and Ram. So as you can see, this technique applied for earthquake forecasting, for studying earthquake events. But in our case, we apply this correlation integral technique to a seismic data study for the first time. On this screen, you're able to see the algorithm for calculation, MATLAB algorithm for calculation of scaling exponent and its double derivative. So here we input some seismic trace, segment it in a different window length. It is our ruler size or a length scale. And after that, we look at from I1 to NW. These are a number of windows. Through the work, we compute the R values, the radius range values, and also we compute the correlation integral. After that, we plot it, the program plots it in a logarithmic scale. And finally, the program calculates the slope of the line and store it. And the slope of this line, it will be our scaling exponent value, or multifractal dimension parameter. After that, when all values are calculated in a particular window length, the program saves this scaling exponent value or multifractal dimension parameter and save it through with a time domain for each segment, and calculation process stops. Here you are able to see the algorithm for calculation of radius range. So first, the program calculates absolute difference between all possible pairs in the sample. After that, the program sorts it sorts the distances in ascending order. Next, program selects the optimum levels of radius range between minimum and maximum values. After that, it counts the number of those distances which are less than or equal to radius range level, repeated for, and the program repeats the same work for all selected unit of radius ranges. And finally, program selects the optimum radius range that gives highest change in count. It means the cluster of points. Let us go through the first part of our work. It is a synthetic traces analysis. So in synthetic traces analysis, our objective is measuring of possibility of the automated seismic horizon recognition method to detect a border between two stratigraphic layers. And also we need to define the window length for the further work, define the minimum window length. Our methodology for our work for synthetic data, we used F3 Netherlands 3D seismic dataset. It is free available in the internet. It's available seismic survey, 3D seismic survey. We used it for our synthetic traces analysis. So we interpreted seismic horizons D0, slump, and D4 that were downloaded from the link given by another paper, Silva et al. In 2019. And we used OpenDetect software for viewing and extracting the seismic data. And of course, we used calculation. We used MATLAB code for calculation of scaling exponent and double derivative. And before this, we used a special MATLAB code for extracting of amplitude data from seismic traces. This is our synthetic data. Here you are able to see the main horizons, D0, slump, and D4, and 5 sets of cross lines. Totally, we have studied 25 traces. So I would before presenting the results, I would like to explain you the calculation process. How is it? So on the left side of the screen, you can see the amplitude values from one particular seismic trace. These are time values in milliseconds with a sample interval 4 milliseconds and amplitude values, positive as well as negative. Let us suppose that we have chosen a window length 5. So we take 5 values of amplitude. And for this set of amplitudes, we calculate a scaling exponent. In this case, it will be 4.8, and double derivative value will be 0.014. So we plot it for time for the time that where this window length ends. It will be time 988 milliseconds. So for the end of this window. So SE will be scaling exponent, and DD will be double derivative values. So we repeat the same procedure, window length 5, calculating of scaling exponent and double derivative, and putting these values of scaling exponent and double derivative for the last time value for the end of window length 5. We repeat the same procedure for each set of 5 values of amplitudes. Again and again, we repeat the same procedure. But as you can see, for the last value, there is no value. There is no value of the last set. There is no value of double derivative, because double derivative requires further value of scaling exponent. Further, there is no another value of scaling exponent. That's why double derivative is not calculated. That's why the values we have the amount of double derivatives derivatives less than the amount of scaling exponent by 1. Let us go further. We combine all these values of scaling exponent and combine all values of double derivative. That is the logic, that is the sequence how we calculate our parameters. Now let's look through the results. For the cross lines, inline is the same everywhere, but cross lines are different. For the set of cross lines from 300 till 304, we are not able to see a trend of the scaling exponent. And as well as we are not able to see the trend for a double derivative. Why? I think it is because the amplitude values are not extremely high. They are mostly uniform, positive as well as negative. But below, for the set of cross lines 375 till 379, we are able to see a trend. Below, for time value 1088, we are able to see that scaling exponent values become lower than in the upper part. It can be connected, it can be correlated with the increasing of amplitude values at the same time interval, at the same time point, because here we are able to see strong positive amplitudes. So we are able to connect strong amplitudes at one time value, at one time interval, and a scaling exponent. On the double derivative, we're still not able to see a trend. But let us go further. Results here, results become more interesting. Here, for interval, for the cross lines 450 and 454, we are able to see this zone of low values of scaling exponent. Here you are able to see it. And also you are able to see the transition zone from negative values through the zero values to positive values of double derivative. And it correlates with the increasing of amplitude values. You can see that in the upper part of the set of this set of traces of cross lines, amplitudes are low, positive as well as negative. And here we are able to see the increasing of amplitude values, positive and as well as negative. And this zone of high amplitude values correlates with the zone of low scaling exponent values and with the transition zone from negative to positive values for double derivative. The same we are able to say about the set of cross lines 522 and 529. The same low scaling exponents, transition zone from negative to positive double derivative, and high amplitude values, positive as well as negative. So we are able to identify horizon slump because it correlates with the high amplitudes. For the set of cross lines 600 and 604, we are able to see the same low scaling, high values of scaling exponent, and are correlated with the zone of low amplitudes, positive as well as negative. And low values of scaling exponent are correlated with the zones, with the zone of high amplitudes, and the same transition zone for double derivative, negative, zero values, and positive. So what kind of conclusion we can do? The zones of the highest amplitude contrast with the most positive and the most negative values correlate with the zones of low scaling exponent values. Here, the high contrast amplitude zone, and here the low scaling exponent values. They are correlated. Next, the zones of low amplitude contrast correlate with the zones of higher scaling exponent values. Here, you are able to see a low contrast amplitude zone, and above these low scaling exponent values, you are able to see higher values of scaling exponent. On the double derivative maps, we can see a transition from negative to positive values with 0 values at the center of the scaling exponent value zones. So at the same time point, low scaling exponent values zone, and it correlates with the transition zone for double derivative. And we have observed that scaling exponent maps with window length 5 show the most acceptable results. And it will be our minimum value, minimum value for window length. Let us go further. We will have a brief introduction to geology of the study area. Our study area is the Parihaka 3D seismic survey, which locates in the Taranaki Basin offshore in New Zealand. Here, you're able to see the location of this survey and where it is located. So we collected information regarding geology of the study area from Arava geoseismic section received from Alco Petroleum New Zealand Incorporated. Here, you are able to see the main formations, the main faults, and the well, Arava 1. So we have found the same signatures in OpenDetect, and that based on the geoseismic section, we did our interpretation. We identified the main faults. It is the Cape Egmont fault zone, giant fault zone, the main formations, and the progradation cliniform unit. So what kind of formation present here in this survey? The first is the giant forceps formation of Pliocene, Pleistocene age, is the thickest housing, is the thickest formation within the seismic survey, which house the paleo channels and progradation clinophores. Next, it is Urinui formation. This is Urinui formation of late Miocene to early Pliocene. Age is dominantly clay stone with interbedded sandstone. Next is the Moki formation. This is the top of Moki formation. This is one. This is the Moki formation of late Miocene. Mostly contains interbedded sandstone, clay stone, and tuff. And the last one is Tikarangi formation. This is the top of the Tikarangi formation, and this is the formation itself of Oligocene to early Miocene age. Mostly contains limestones. And let us show you the results that we received. Totally, we have studied three in lines and one cross lines with step 100, and totally 48 traces of the Parihaka 3D seismic log we studied. By using scaling exponent, it was possible to detect different features in 77.3% of cases, and by using double derivative, by 44% of cases. Let us look through the scaling exponent results. So what we can identify is the on the scaling exponent map is the strong anomaly below the bright spot A, and below the bright spot B. Also, the lower part of the giant forceps formation, it is the progradation clinoform unit, express the higher values of scaling exponent. And the top of Urinui formation and Moki formations are identified by low values of scaling exponent. I suggest that it is due to higher values of amplitude, positive and negative, on the top of these formations. And the same signature we are able to see on in line 2600. The same very strong anomaly on the zone below the bright spot A, and on the place of the progradation clinoform unit, where this strong anomaly is observed below the bright spot A, but on the place of Tikarangi formation. And we are able to identify the top of Urinui formation and Moki formation. And not directly, but indirectly, we are able to identify the presence of Cape Egmont fault by changing of scaling exponent values. Next, we are on the inline 2510. We are able to see a strong anomaly. It reaches scaling exponent values 20 and even more than 30 in some places on the place of the progradation clinoform unit. Also, the fault zone could be identified not directly, but through changing of shape of the reflectors, by changing of shape of the scaling exponent values. The same, we are able to see the top of the Urinui formation and Moki formation. For our cross line 4470, we can see the same very strong anomaly below the bright spot A. Values values of scaling exponent become more than 30, and the same the progradation clinoform unit exhibits the higher values of scaling exponent, and the zone of this unit highlights with the strong anomaly. Also, the top of Urinui formation and Moki formations, they are visible. Let us look through the results from the received from the study of double derivative. For inline 2657, we are not able to see strong identifiable marks, but we can see the higher values of positive and negative values of double derivative for zones below the bright spots A and B. And on the place of on the top of the Urinui formation, we are able to see the negative values of the double derivative. But for inline 2600, we are able to see the interesting picture. We are able to see the interesting trend. Of course, the values for the zone below the bright spot A shows the high anomaly amplitudes, high anomaly, positive as well as negative. And the progradation clinoform unit appears on the double derivative map by a transition zone from positive values to negative values. It may be, it may be connected with the less compacted sediments for the progradation clinoform unit, and it it is expressed in amplitude and consequently in the scaling exponent and double derivative. But for the inline 2510, the main anomaly we are able to see for the zone under the progradation clinoform unit. It is the brightest anomaly for this map. The progradation clinoform unit reflects as a zone, as a transition zone from very strong positive values of a double derivative to very strong negative values of double derivative. For the cross line of 4470, the main interesting features that we are able to observe, it is the strong amplitudes, positive and negatives, for the zone below the bright spot A. And the progradation clinoform unit zone is expressed by the also by the transition zone from positive through negative zone. And after that, it goes to a positive zone again. So which is a mark that could identify the Urinui formation, the top of the Urinui formation with the high values of amplitudes, positive as well as negative. This is another representation of our results. We took one particular seismic trace with from inline to 1510 and cross line of 4570. We are able to see the same trend. For example, the progradation clinoform unit zone, it shows low values of amplitude, and it expresses very high values of scaling exponent and a very strong transition zone from positive to negative values. So the progradation clinoform unit is very identifiable. Next, when we cross the Urinui formation, we were able to see the very high values of amplitudes, positive and negative, and it correlates with the low values of scaling exponent. After that, amplitude values, they become more flat and not so prominent, not so high, and it expresses in scaling exponent graphs with the increasing of scaling exponent values. Again, when we cross Moki formation, we see very strong, very high amplitudes. And again, the scaling exponent values become low. And for Tikarangi formation, amplitude values become smaller, and scaling exponent values become higher. And if we see a very strong increase of scaling exponent, of course, or increasing of or decreasing of scaling exponent, of course, it expresses in double derivative maps with the strong increasing of a double derivative. And in such case, we are able to see very strong positive and negative peaks. But the main idea is when we see small amplitudes, we are able to see high values of scaling exponent. And on the zones of strong amplitudes, high amplitudes, we are able to see low values of scaling exponent. And it's time for making conclusions. So on the scaling exponent maps, it is possible to define borders between stratigraphic layers, loose and dense sediments, because they express different values of amplitudes. And by such way, it is possible to identify the borders between different stratigraphic layers automatically through their amplitudes. On the scaling exponent maps, zones below the bright spots A and B create very strong anomalies. The progradation clinoform unit creates a strong anomaly on the scaling exponent maps and showed transition from positive to negative anomaly on the double derivative maps. It is very strongly identifiable. Faults can be detected, but indirectly by using scaling exponent and double derivative, where I think it is possible to detect faults, but indirectly through shifting of borders in stratigraphic layers and scaling by shifting the negative values of scaling exponent. Scaling exponent can be used for identifying loose and dense sediments on the seismic section. Double derivative the double derivative identifies well borders between layers, and it identifies the borders as well as strong the increasing or decreasing the scaling exponent values we can see. And about our future plans, we studied this technique. We applied this technique in post-stack 3D seismic data. In the future, we want to apply the same technique for the pre-stack seismic data, pre-stack 3D seismic data. This is our future plan. So thank you for your attention. I finished it.